The conversation with Professor Valentin Troll. We are very lucky to have him on board. Please give him a warm welcome to the stage for his conversation, The Youngest Ocean on the Planet and Making the Atlantic.
Thank you so much. Thank you for the introduction. Thank you for joining me this afternoon. If I had my free choice, I would probably curl up in my bed right now with that swell. But no, my daughters gave me these sea bands, and they do miracles. So I feel quite up for the challenge now. And I'd like to talk about the youngest ocean on the planet, which, of course, is the Atlantic Ocean. And it's, of course, a major ocean. It's a big ocean, but it's nevertheless a youngster when it comes to the oceans of the world. Well, it's the second largest ocean, despite being the youngest, and it covers about 20% of the Earth's surface. And it hosts about 29% of the Earth's water. And, well, it stretches from, let's see, does this work? Can't see a pointer, but we'll make do without. It stretches from the southern tip of South America all the way up to Iceland and Greenland and even further north. And it's, of course, separating North America from Europe and Africa from South America. And it's the youngest of the 5 main oceans, and it started to form in the Jurassic period. This is back when the dinosaurs roamed the Earth some 150, 160 million years ago, and it followed from the breakup of Pangaea, the entire Earth, and there was a supercontinent back then. I should point out that the Earth evolves in supercontinent cycles. Before Pangaea, there was a different supercontinent called Rodinia, but let's not go too far right now. And there was a time back prior to the Jurassic where all the continental landmasses were united. And this was Pangaea. Well, just to give you a flavor, the United States is less than 1/6 of the size of the Atlantic Ocean, and the Atlantic Ocean is generally agreed upon to be the first major ocean that was crossed by plane and by ship. And we'll talk a little bit about that later on as well. So here's the Atlantic Ocean, and the pointer, I think here on the black we'll see it, but not elsewhere. So it's marked by this spine, this geological spine, the mid-Atlantic ridge. And this is where the Atlantic spreads, and it spreads very gently with about 2 centimeters a year. The Pacific being a much older ocean, and the Pacific being a really mature ocean, it spreads at about 7 centimeters a year, so the Atlantic hasn't actually geared up to full speed yet. So this Pangaea idea of the supercontinent Pangaea goes back to this gentleman here, Alfred Wegener. And he was heavily criticized for this back in the days. He postulated this 1915, 1910, round about that turn, so well over 100 years ago. And he argued that the continents can be moved together. They fit like a jigsaw puzzle, and they drifted apart, and he called it continental drift. The major criticism he received was for a lack of a mechanism. People said, how would that work? Back then, there was no understanding of continents moving laterally. And he pointed out that there was fossil evidence. There's fossil species that continue over South American borders into Africa. And he argued these must have been provinces that were together. And he made similar observations with fossils from South America, Africa, Antarctica, and into Australia. And this was one of his main line of evidences where he said, look, these things were joined in some giant landmass. And only in the 1960s, 1970s did his ideas get fully accepted. And it started off some 100 million years ago. There's a little reconstruction starting there with 80 million years ago. Once the Atlantic started to form, it drifted these continents apart, and eventually a proper ocean formed. So here we see Pangaea in the top left as a unified landmass, and then it's split up into major continental blocks. La Russia is nowadays North America and part of Asia, and Gondwana being South America, Africa, and Australia. And eventually these continents are drifting apart to form what we see at the present day. If this theory is correct, then some point in the geological future, all these continental landmasses will come together again, and they will make another supercontinent before it splits up again. So, but this is very far in the future, and here we can look at the age of the lithosphere, the age of the rocks underneath, and you see Greenland and Scandinavia here in the top left of the grey and black panel, and there the red is young material forming, and their spreading started some 100 million years ago, and it's still going strong, and Iceland sits right there in the middle, and you see in panel F, Iceland is actually at the youngest part of this spreading center in the North Atlantic. So how does this spreading go about? Well, there is these spreading centers, and they span through all the major oceans. It's a ridge system that's about 60,000 kilometers long, and it hosts some 85% of all the Earth's volcanism. So the volcanism we see on the continents is only about 14, 15, 16% of all the volcanic activity on the planet. And here in the Atlantic, we see the spine going down all the way. It wobbles a little. It's not a straight line. It's marked by many little faults. We call them transform faults that shift the ridge laterally a little bit. But it goes through the entire Atlantic. And at these spreading centers, the hot mantle is welling up, and it pushes the plates towards the left and the right, and this is where magmatism then takes place. So we know about this spreading because when rocks form, igneous rocks, magmatic rocks, they contain tiny little minerals of iron oxide. And the iron oxide will actually orient itself according to the magnetic field. And the magnetic field is changing throughout Earth history. And depending on when the rock solidifies, we have positive or negative polarity in the rocks. And if you do a magnetic map of the oceans, you actually find it's stripy because the rocks have formed at slightly different times. And this is the stripy pattern here in the center image, where the fresh rocks would have a certain polarity, and somewhat older rocks that have already been pushed away have a slightly different polarity, and yet older rocks that are yet further away have yet again other polarity. So these mid-ocean ridges forming 60,000 kilometers of ocean ridges, and as I said, they host some 85% of all volcanism on Earth, and there is an eruption almost any given point somewhere along this system. So initially, these things start up as little continental rift zones, as continental breakage zones, and eventually they widen, and then finally they make oceans. And we, in geology, we work with analogs, and one good analog for a continental rift is the East African rift, as you see in the top right here. That's where we are breaking a continent apart. Another one of those is actually the Rhine and Rhone Graben in Europe, where Europe is breaking apart. But it's very, very slow, and the European one, well, there's good chance it might get arrested. It might actually never become a real ocean. But the East African one, it starts to make an ocean because we have the Afar Triangle, and the Red Sea is actually where water has already crept in. This is where the spreading has continued to a point that an ocean is in the making. And eventually, once the spreading has continued for many millions of years, there is a real ocean like the Atlantic. And we talked about Iceland being a very special case, being a plume that pushes up a ridge, and therefore we can see it. And in Iceland, we see this ridge system on land. So here, the lower two images showing the breakage zone, the fracture zone that is exposed on Iceland, and it's a large regional feature, very impressive. And on the western side of Iceland, you're of course on the North American plate, and on the eastern side of Iceland, you're on the Eurasian plate. So, why in Iceland? Well, I mentioned it, it's because Iceland is a bit special. It's not just the ridge, it's also this anomaly, this heat anomaly coming from deep inside the earth and pushing up. We call it a mantle plume. Some people like to call it a hotspot. Some researchers even think there's a difference between a mantle plume and a hotspot, but that's a bit of semantics if you ask me. And the Iceland plume is going strong for quite some time, at least 70 million years. And there's some reconstruction here. Initially, the Iceland plume may have had two arms. We talked about it very briefly. But nowadays, it's got one major stem, and that sits under Iceland. And it produced a lot of rocks that are now exposed in the ocean. It makes the Iceland-Faroe Ridge on the one side and the Iceland-Greenland Ridge on the other side. And the gray areas here in that map, they are the submerged volcanics from the Iceland hotspot. They are now underwater, but they are elevated banks of materials that are of magmatic rock, and they go back to previous activity of the Iceland plume. So, but the beauty about Iceland is you can walk inside this mid-Atlantic ridge, which otherwise is always underwater. And if you follow towards the coast of Iceland, you'll actually see how the water creeps in. And you can actually go even further. And if you are bold, you can even dive in there. You can dive in the mid-Atlantic ridge. And if you're super bold, you can go very deep there. I've never done this. But here we have divers exploring the fracture zone of the mid-Atlantic ridge of Iceland. And you can go quite deep if you want, I'm told. And eventually, if you were to follow this all the way down to the ocean floor of Iceland, you would come to the main ridge system at the ocean floor in the center of the Atlantic. And the Atlantic is about, on average, 3,300 meters deep. And the deepest point is actually off Puerto Rico with 8,600 meters. Most of the mid-Atlantic ridge is actually at about 3 kilometers depth. So this is like a mountain zone underwater in the Atlantic. It's not very deep, it's actually elevated. And here in the lower left, you see that there's this elevated ridge system that sits in the middle of the Atlantic Ocean, and this is where most of the spreading happens, and this is also where most of the volcanism happens. So, now, this is of course something we're researching for many years, and just this morning I went into my little picture library. So I've sailed on several research ships, like here the Poseidon and the Meteor, and I remember that we had some rough days there as well. So I put these top right-hand pictures in there for you to show you it's not quite so bad today. I've seen worse. So, and I didn't have any sea bands back then, I tell you. So, but here we can drill down into the ocean floor. We also have submersibles these days that take us down there. They can withstand the pressure, and they can actually take photographs, and they can take water samples, and they even can take rock samples from down there. So, and this gives us a good idea of how the mid-Atlantic ridge looks like. And in the lower right hand, there's an image of this little fracture system on top of this ridge. And there we have magmatism. We really have little submarine volcanoes there and little lava flows. And there is a little magma reservoir sitting underneath. And it produces little fissure eruptions and also, as I said, little volcanoes. And let me stress, we know from Iceland that a lot of volcanism on Iceland happens along fractures, and this is exactly what we need to expect from the mid-Atlantic ridge as well. On the left, I'm showing an image from the 2022 eruption on the Reykjanes Peninsula, and you can see that the lava comes up along a fissure, along a fracture. And then here's an image from the ocean ridge at 3,000 meters depth, and here's one of those fractures, and we see lava rock on either side of it. And every now and then, submersibles are happy enough, and they catch a little eruption. And of course, much to the excitement of the crew on on the ship, then of course one has to be very careful to bring the submersible not too close, but not too far away either. But here in the top right hand, you see the arm of the submersible, and you see a little bit of lava pouring out, a little pillow lava arm that comes out, and of course it quenches immediately on the outside, making a dark crust. But when the crust is ripped apart, you can see the glowing material inside. So here are a few images of what it looks like under the ocean. And here is again one of those fracture systems and magmatic rock on either side. And this is in the crest of the ridge, of the mid-Atlantic ridge. And I showed one of those before. Here is a tongue of lava that is erupting. And we also have these smokers, as people call them. There is no smoke, of course, you're underwater. But this is hydrothermal fluids that are emitting, and we're distinguishing between white smokers and black smokers. I'll talk a little bit later about this in more detail. The white smokers have often tiny crystallites of calcite and silica, and the black smokers have tiny crystallites of metal deposits. So, and this is actually very important for potentially resolving some of our resource issues in the future. So here are a few shots from deep under the ocean. There's often pillow lavas because they look like, well, pillows, but this is quenched lava because when water gets in contact with the hot lava, then the lava freezes up and it flows in little tubes, making these pillows. And here in the lower part, we have a bit of a pohoi texture, a ropey lava, and the one in the top right, we have a more flat-lying surface of lava. And here we have pillow lavas, and of course they get fractures. And if you crack these pillows open, you see they have radial cracks, radial joints. Many of you have probably heard about the Giant's Causeway. This is a basalt lava with columnar jointing. This comes from cooling. Then the lava shrinks a little by 10%, and that means it cracks. And the cracks and the columnar joints are usually perpendicular to the cooling surface. And here, the pillows cool all around, so that means the cracks are actually perpendicular to the outer surface where the cooling happens. The picture in the lower right is very nice because there we have a pillow that then solidified and then eventually cracked open, and another arm or tongue of lava came out, and you can see that there. So this is how these lavas progress. They freeze over, and then they break out again, and freeze over and break out again. So, and here we have a few more images, and this is the arm of one of our little submersibles that takes samples, and this is usually done remotely. There is some where people sit in there, but for the really deep work, we usually don't have manned submersibles. We usually have automated, remotely controlled submersibles. And here's more pillow lavas. Let me stress there is a lot of submarine life in those areas as well, and these rocks are very quickly colonized, believe it or not. And here's a few more images. This is a very intriguing feature. This is actually lava crusts, and there must have been gas involved underneath. So this is lava crusts that have been inflating because of gas pushing this material up, and there's pillars of material in between the former giant gas bubbles. And if you take a sample from there, like in the bottom right, you see that the lava was still liquid and was pushed apart into these tiny little needles before eventually many of these needles would break and only some of the stronger pillars remain. This was a big mystery when the first submersibles brought footage from down there. And of course, initially people said, oh, Atlantis, a sunken city, but this is actually a very natural phenomenon. So I talked a little bit about this, black smokers. This is hot vents because when water creeps into these fractures and gets close to the magma source, the water will heat up and it will leach elements out of the surrounding rock, and the hot water then rises up, and when the hot water gets in contact with a cold seawater, you have a chemical reaction. A lot of the minerals that are dissolved in the hot water will start to precipitate. And it looks like smoke, but it's actually zillions of tiny little crystallites that form because of the temperature and pH contrast between the hydrothermal fluids and the ocean water. Here's a white smoker, and depending on what minerals are forming, the smokers have different colors, but as I said, there is no smoke involved. It's actually a chemical reaction involving mineral precipitation. Then, I'm not a biologist, so I don't want to go into a lot of detail here, but some of the ocean floor communities are quite astounding. And this is also where scientists have discovered archaeobacteria. Now, it turns out they're not bacteria at all. They are part of the group Archaea, and these are single-cell organisms that live there, and they love the heat of the volcanic activity. And they digest energy from these systems, and it's believed that they could have been some of the very earliest life forms of our planet. And here's some images, and they are very happy at 190 degrees Fahrenheit and down to 0.9 pH. Very acidic conditions, very hot conditions, almost boiling point of water, and these little chaps, they're very, very happy there. So, having a look at the center of the ocean, we just looked at this red spine of the Atlantic. I also like to talk a few minutes about the margins of the Atlantic. So, what happens at the margins? Well, when the ocean drifts apart, when the ocean spreads, then the margins on either side are initially passive margins. Nothing much happens at them, apart from the fact that we might have some instabilities, some landslides. And here where it says in our top left panel where it says sediments, this is the passive margins. And all of Norway has a passive margin. And we'll talk a little bit more about this over the next few minutes. Passive margin means there is no volcanism, there is no major activities, but material is usually shed from there into the ocean basins. And this can be in form of very small drizzles of material, or it can be in form of large, large landslides. And there's evidence for a very large landslide that came off Norway several thousand years ago. And this is the Storegga slide, or slides, depending on whether you want to see this as one event or several events. And the red area in the map to the right, that's the Storegga slide. And it came off the coastline of Norway along the passive margin, and it created a tsunami that caused tsunami sediment deposits in the Shetlands, in Orkney, in the Faroes, and several tens of centimeters thick and several tens of meters above the shoreline. So this must have happened about 6,200 years ago, and it probably involved a 290-kilometer long section of coastal shelf, and it produced a volume of some 3,500 cubic kilometers of material that was slumping into the ocean. So if this would happen today, it would be quite a disaster, because it would affect most of the coastal areas in the region where we are sailing just now. So, but I should point out that mature oceans, they are not just spreading, mature oceans are subducting at the margins. And the Pacific is often also referred to as being surrounded by the ring of fire. You have subduction, old oceanic plates are sinking under their own weight after a certain amount of time, and then they're sinking back into the mantle, and this is called a subduction. The plates need to be pretty old for that, usually about 180 million years. Then they are mature enough to sink back into the mantle, and the Atlantic has almost no subductions at its margins, showing us that the Atlantic is still a very, very young ocean. There is one exception, and that is very intriguing. It's a wonderful natural laboratory, and that is the Antilles, the Lesser Antilles here, because their subduction in the Atlantic has just started. We have an island chain. This is the Lesser Antilles, some beautiful areas there, Guadeloupe, Martinique, Dominica, etc. And this is where we have the oceanic plate, the Atlantic plate, submerging under the Caribbean plate. And this gives rise to a different type of volcanoes. Now, one of the exam questions that we sometimes ask for our fourth-year students is, what will happen along the eastern and western seaboards along the Atlantic margins? And then our geology students have to think about what will happen in the future. And the answer is, there will be subduction zone volcanoes all along the margins of the Atlantic in the next 20, 30 million years. So geologically, this is what we would predict. And indeed, this is what I think will actually happen with the margins of the Atlantic in millions of years to come. So here's a little diagram. It's very complicated. I don't need you to go into details at all. But here the Atlantic Ocean spreads with 2 centimeters a year. It's pushing against the Caribbean plate. And of course, scientists are really excited. This is why I'm showing this, trying to unravel all the processes going on and how these new subduction zones form. And that gives us a lot of information to predict about more mature systems like the Ring of Fire in the Pacific. So, I talked about plumes. Well, we looked at mid-ocean ridges now. We looked at subduction zone, and I'd like to bring you back to plumes, like the Iceland plume, just for a very quick minute. And the Atlantic is actually littered with plumes. And in the map to the top right, all these yellow-red dots, they are little plumes. And of course, Hawaii is the archetype of a plume system. But here in the Atlantic, we have a few as well. There's Jan Mayen, there's the Azores, there's the Canaries, there's Santa Helena, where Napoleon spent the rest of his life, and Tristan and several others. And here I have a little map from the Canary Islands where we see the ocean magnetic anomalies. They're marked with ages. And here we have a plume track cutting across. So there is a stationary heat anomaly, and the plates are moving ever so slightly. And this is like a Bunsen burner underneath a moving object. And it gives rise to these little island chains that we see also in the Atlantic. In the Pacific, the island chains are much more strung out because the plates are moving a lot faster. In the Atlantic, they're more clustered. And here's another example just from a little bit further south in the Atlantic, the Whalefish Ridge. And here's a little island called Tristan da Cunha, TDC abbreviated here, sits close to the mid-Atlantic ridge, and it gave rise to a whole track of little islands and submerged little volcanoes that span all the way to Africa. And here we have these plume tracks in the Atlantic as well. So Iceland is not the only one, but Iceland is the most prolific one. So let me summarize the geology before we move to human travel on the Atlantic. And here, a good, really mature ocean has 3 types of volcanoes: rift volcanoes, plume volcanoes, and eventually also subduction zone volcanoes. And the Atlantic has rifts and plumes, and also just the very first subduction zone volcanoes in the Caribbean area. And this is signaling that the Atlantic is just about coming of age now when it comes to become a proper ocean. So, but I'd like to spend a few minutes now on human interaction with the Atlantic and the crossing of the Atlantic. Well, we all know the Atlantic separates the old world from the new world, and here various attempts of traveling across have been made. Usually Christopher Columbus is accredited with making the first passage, but most likely he was not the first human to cross the Atlantic. And he was probably the most famous one for a long time, but there were several attempts before him. I should point out Thor Heyerdahl, and maybe you have the opportunity to see the museum in Oslo. He believed that there was the opportunity, for example, for Egyptian cultures to travel across the Atlantic in papyrus boats. And he tried to simulate this. He built the Ra-1, and Ra after the Egyptian sun god, and he made this from papyrus, and he sailed across the Atlantic. The Ra-1 never made it. It actually sank. So he believed that he can do better, and he built the Ra-2. And he managed to actually bring the Ra-2 into Barbados in 1970. And he showed with this experimental type of archaeology that in theory people from the old world could have crossed the Atlantic already thousands of years ago. There was never any real evidence to show that any materials from the old world had been brought over to the new world. There is no archaeological evidence. So while in theory it could have been possible, there is not a lot of evidence that this really happened. Now, you may have heard about St. Brendan's journey, and St. Brendan was an Irish monk, and he traveled with a cowskin boat. It's not believed that he reached the Americas, but he reached what is known as the Blessed or Fortunate Isles. And it's not quite clear what islands they were, and some people say it could have been further down south in the Atlantic. Other people say it was Iceland or some other place like that. But St. Brendan, he traveled in the 500 AD area, and he reached these islands where he describes rivers of gold fire and great crystal pillars. Now, how much of this is just imagination and how much is reality, we don't know. But he also describes these as blessed islands. I don't think Iceland would have qualified for that at the time. So I think more likely he reached the Azores or the Canary Islands. And that would have both been kind of, on the eastern side of the Atlantic, maybe in the center of the Atlantic. Some people speculated it could have been the Faroe Islands, but there was no volcanic eruptions in the Faroe Islands for many millions of years, so I don't think they are really good candidates either. Then, of course, there was the Vikings, and the Vikings were very experimental. Eric the Red, he was living on Iceland, but he didn't get on with other folks so well, so he was made an outcast. He had to leave for 3 years. He was exiled for 3 years. And where to go? Well, he didn't want to go back to Norway, so he settled further west, and he built the first settlement on Greenland. And he returns to Iceland later on to attract more settlers, and he was a smart, cunning chap, and of course, he didn't call it the land with a big glacier, he called it Greenland, so making it sound very attractive. And indeed, there was settlements then later on, but they didn't last, they didn't survive. And his son, Leif Erikson, he went even further towards the west, and he is accredited with discovering Vinland, which was probably present-day Newfoundland. And there is some archaeological evidence. There has been some Viking artifacts found on Newfoundland, so there's a good chance this story is actually real. Then, of course, Christopher Columbus, and he was Italian, but he was in Spanish service, and he sailed under the Spanish banner of Queen Isabella, and he wanted to discover Asia and India because he wanted to create new trade routes. I read up quite a bit on him, and he had some very intriguing encounters on the way. Apparently, he even had an affair with the governess of El Hierro, one of the small Canary Islands, and Queen Isabella got so unhappy about this that there's a letter saying, "Mr. Columbus, can you now sail off, please?" And eventually he did sail off after claiming he had to repair his ships multiple times. But he went out there. And at the time he was believed to be a great sailor. And later on, scholars later on, they questioned that a little bit. They speculated that maybe he wasn't quite as great a sailor as he made himself sound in his logbooks. So here's the evidence for that. The upper map here is how Columbus viewed the world, with the Americas being a shaded blue, light blue area there, and the orange colors being the world as Columbus imagined it. So sailing off from Iberia and northern Africa towards the west would have ultimately brought him to an area in Asia. That's what he believed. And to his last breath, he believed he actually reached India. He never understood that he actually discovered the Americas. He did several journeys, and the fourth voyage is marked in yellow here in the lower right-hand map. And he traveled backwards and forwards multiple times. And note a pattern. Usually his travel westwards was further south than its travel back to Europe. So it was like a flat-lying circle that he did multiple times. He believed that it was his skill that allowed him to do that, but of course the reality is there's an ocean current. And I think with a bit of luck, he just hit this ocean current that brought him towards the Americas and back. So here is the North Equatorial and the Gulf Stream ocean current. And this is exactly how Columbus sailed. He went down to the Canary Islands, and from there he went westwards, and then he came back a little bit further north, hitting Iberia again. And this is why some people say maybe he wasn't the most skilled sailor, maybe he just was a very, very lucky sailor. So, a few words now about more modern times, and this is the transatlantic telegraph cable. I thought I'll say a word about that. This was going back to the 1860s and the 1850s. In fact, that's where the first attempts were made. A transatlantic telegraph cable was laid, but the first one was actually very poor, and it had to be replaced within less than 10 years. But it was a huge effort, and large cable ships were bringing these cables across the Atlantic. And initially, the cables broke quite frequently, and strangely enough, they often broke over the mid-Atlantic ridge, because nobody had any idea that there was volcanoes down there. Well, they learned, and eventually better routes were found, and in 1865, a really good, strong cable was laid, allowing speedy communication between the old and the new world. Then, of course, eventually, we developed other means of transport, air travel, and I should, of course, mention Mr. Lindbergh, Captain Lindbergh. He flew across the Atlantic, and he flew to Paris, and this was, of course, a great feat, and it took him 33.5 hours. Well, these days, if I fly for 33 hours, I end up in New Zealand, so there's quite a difference there, but for him, this was, of course, a great adventure, and, well, he's still remembered for this outstanding achievement. A little while later, this person, Amelia Earhart, she set out to do a similar thing, and of course she was the first woman to achieve transatlantic flight, and she was actually a lot faster, but she also chose a shorter route. She was quite nifty about this, and she did it in 21 hours. And here is a few images of her, and she traveled from Newfoundland to Wales, and she received the US Distinguished Flying Cross for that, which I show here. Tragically, she went missing on her, well, all-around-the-world flight in 1937, and to this day, we actually don't know where her plane went down. So this is an old US stamp, and maybe some of you remember it. This, of course, shows her and the airplane in the background. Now, one of those more tragic chapters, and this is the Battle of the Atlantic, and this was, of course, in the Second World War, 1939 to 45, and large convoys with supplies were coming over from the US towards the British Isles in particular, and this was strategically extremely important for both sides in the war, and there I'll show a little map here. The issue was crossing the Atlantic was quite possible, but the Germans, of course, they had these U-boat packs, and air cover was a real issue. And here in the upper diagram, you see these circles, these blue circles. That's the reach of the airplanes. And the red dots are sunken freight ships, and the dark little crosses are sunken U-boats. And you know exactly where most of the freight ships were sunk, and that is where there was no air cover, while most of the U-boats were actually sunk close to port where airplanes could reach them. Very intriguing distribution of things, and this was actually why Iceland was so extremely important. And this is why Britain actually occupied Iceland at the time, so that they could extend the air cover over the Atlantic. So, I like to close with the last few minutes about something else, and that is the search for Atlantis. I can't talk about the Atlantic without Atlantis. And here we sometimes see these news somebody searching for the long-lost continent under the ocean, which is Atlantis. It goes back to the Greek mythology, and I'm showing this here. I don't read Greek, but I have a Greek PhD student, and he helps me with this, so he comes with these wonderful Greek names, and it goes back to about 450 BC, where the Sea of Atlas, the sea beyond the pillars of Atlas, beyond Gibraltar, that gave rise to the name of Atlantic. And it's believed that there was a land beyond the pillars of Hercules, Atlantis, as Plato described it. So, and where was this exactly? Well, Plato says, there was a big peak standing out, believing it's the peak of a mountain that sank. So it gave rise to the idea that maybe the Azores Island, which have a big mountain called Pico, may be the place. And this would be right in the middle of the Atlantic, but indeed off Gibraltar. So here's various hypothetical maps, and artists get quite inspired by this sunken world of Atlantis. And if you look up on Google and if you search the internet, there's various types of reconstructions. Some are incredibly detailed. I don't know how people do that. But yes, so you will find many of them putting Atlantis actually into the center of the Atlantic, round about where the Azores are. And here's just a few more impressions. A sunken continent sitting there off the west coast of Africa. And the map to the left is actually with the north arrow pointing downwards. This is why America is on the right, and Africa and the Iberia Peninsula is on the left. So, and Plato describes a circular structure, and here is an artist's impression of how this could have looked like, the world of Atlantis. And every now and then you see newspaper headlines that somebody has actually discovered Atlantis. But I need to point out that this area, the Rockall Trough, is actually where we have these old rocks from the Iceland plume, and I don't think it's Atlantis. The geologists know better on this one, but it makes for these spectacular headlines, and they're not quite to be taken all that seriously. So here I'm showing this map again. I showed it earlier. The grey area just off the British Isles is the old rocks from the Iceland plume, and this is where these people here on the left had a slight confusion about geology and mythology. But having said this, there is a sunken land. And actually, Plato may have heard about this, because this is what we call Doggerland. This is an area between Scandinavia and the UK and mainland Europe, the Netherlands and Denmark and northern Germany. And this area was actually above the water some 6,000 years ago. We are sailing on it right now. It's beneath us. And fishermen have brought up mammoth skeletons like the one in the lower right from that area. So there was animals, land animals living there. And there is even seismic evidence for built structures down there. And this has all to do with the Ice Age. Back in the days when most of the water was locked in the large ice sheets, the sea level was lower and therefore more land was exposed. And this area here was very fertile land, we believe, and it allowed the early Britons to walk to the British Isles, which were no isles, of course, back then. So here's some reconstructions of Doggerland, and of course, with the melting of the ice after the end of the Ice Age, Doggerland drowned. And this may have been some of these legends that went all the way to Greece. And so Plato may actually have described a sunken land well out there in the Atlantic, but he couldn't place it. So this is where some of the legends may have actually, well, they might still have a true core, but it wasn't out there where the Azores are. It may have been up here in northern Europe. So here is a scientific reconstruction. Again, we don't have to go into the details, but the map on the right shows the extent of the ice sheets during the last major ice age. And once the ice sheets were melted off, there was, of course, water rising, and then Doggerland drowned, and we still have the Dogger Bank out there, an elevated area in the North Sea that was on land some 6,000–7,000 years ago. So I close off with the last few words about treasures in the Atlantic. And of course, there is no treasure in Atlantis, it's sunken, but there's actually a lot of ore deposits down there in the ocean. And there's two main types. And one type is actually producing a lot of copper. And this scheme on the right here shows that if we electrify our traffic, a lot more copper will be required in the future than we are producing at the present day. And we're not quite sure where this copper is supposed to come from. But one option is going down there into the ocean crust and into the crest where the volcanoes are, because these black clouds, these black smokers, they produce a lot, and I mean a lot, of copper. So these mounds there, they are actually made of sulfides, copper and iron sulfides. And here we see some of them, and we have taken samples. We know this is reality. So there is vast amounts of ore deposits at the ocean floor, iron and copper sulfides. We just don't know how to get them yet, but they are there. And the first attempts of drilling them have been made. So the idea here is that fluids are creeping down along these fractures. They heat up, they leach these metals out of the rock of the ocean floor, and then they're expelled again at the surface. These fluids then come at 350 degrees, and they're very acidic, and they hit very cold ocean water that is alkaline in chemistry, and so it causes a precipitation of all these minerals on site. There's only two metals that don't precipitate right away, and that's manganese and cobalt. Manganese and cobalt, they travel in the water for some time, and then they precipitate elsewhere. And cobalt, as you know, is very important for making batteries for electric vehicles. And at the moment, we have a shortage of cobalt. And then on the ocean floor, we form these dark crusts of manganese and cobalt. And here's an image of one of those crusts on a rock from the ocean floor. And this is something that the European Union is now investing in to potentially mine. So here, again, a diagram giving you a prediction of our cobalt demands up to 2030. And the red circle shows us that there's a huge deficit of cobalt that we're expecting will hit us very soon. And therefore, new sources of cobalt are really, really needed. Now, the ocean floor is littered with these little nodules, manganese and cobalt nodules. Well, they usually have a core of something else, a little rock fragment, but then there's precipitation of manganese and cobalt surrounding them. And the deeper into the water you go, the more of those you find. So there's literally vast fields near the surface of the ocean floor made of those nodules, these manganese and cobalt nodules. And here, if you cut them open, you see that there's a rock fragment inside. It's only a coat of this material. And there's now big ideas about how to get this material up. We don't think that there will actually be people going down there. It might be more giant hoovers or so, like this potential construction here, where a drill ship is bringing down a steady system of pipes that then allow to hoover up material from the ocean floor, and this might allow us to get material up. But of course, there's a lot of speculation. It's very early days, and there's a large Dutch project now funded, and they're thinking about these caterpillars that are driving on the ocean floor. As you see, it's an artist's construction. It's not reality at this point, but there is serious thinking going on about how to produce this material for our industry, how to retrieve it from the ocean floor. So, will there be deep-sea mining for manganese and cobalt nodules? Well, I don't know, but of course, we must be realistic. There's a large risk for ecosystems on the ocean floor, and not so much for the big ones, but for the microfauna down there. And some of these creatures we don't even know about at this point, and we might be risking their existence in the long run. So this is part of the discussion, and Greenpeace has issued this cartoon here, where of course they're showing quite vividly that in our attempts to save the environment, we're actually destroying part of the environment. So this is a discussion that needs to be had, and any submarine mining will have to take this into consideration. So, and this lets me close with one of my favorite authors, Jules Verne, because he lived quite a while ago, but he was so perceptive. He understood that there's volcanoes under the oceans, although he never saw them. He also understood that there was resources under the ocean, because Captain Nemo got his wealth from mining submarine resources. And he also knew that we will have to struggle with submarine life forms, although the ones he pictured were much bigger than the ones we have to worry about today. Thank you very much.